안녕하세요. 굿모닝. 네, 안녕하세요. Okay, so welcome to the last week of AI504. Well, actually, last week will be next week, which is the project week, but before that, so this will be the last course. So today we're going to talk about image text multimodal learning. Okay, and well, I mean, not a lot of people are here, but still, like, since you're here, please pay close attention to the material today and the practice session that you'll be doing this Thursday, because project three will be based on this week's course, the theory session and the practice session. Right, so there's a bit of a lag. I guess it'll get better. Right. So we used to do a bit we used to go a bit deeper into the old vision text multimodal learning, such as show and tell or text condition GAN, DALL-E 1. But since time has passed and a lot of new techniques have come up. So we're actually ditching show and tell in the old ways, and we're briefly going to touch upon show attend and tell, which is, well, not a lot of, I guess, practically nobody really uses this old architecture anymore, show attended tell, but still it's one of the seminal work that started the whole thing back in 2015. So might as well just, briefly skim through the details. And then we're gonna go to text to image. We're gonna look at clip and DALL-E 2, which are both from OpenAI. And then we're gonna, if we have time, we're gonna study a little bit about the BERT-based models. So between 2019, 2020, 2021, a lot of multimodal learning came up, which were all based on BERT. So we've already learned BERT like several weeks ago, which was all based on mask language modeling. So you can actually put two modalities into the transformer encoder and do the mass language modeling still and get a pretty good relationship learned by the BERT model between vision and text. So we're going to take a look at that. And then finally, the modern day vision text multimodal learning, which is vision LLM. Right. So image captioning, there was something called image to text. So vision image captioning was probably the most earliest work that tried to do multimodal learning between text and vision and text. So given an image, we want to translate it into text. So it's kind of like uh, French English translation, but rather giving French, you give an image to the model, and then the model translates that to language. So that's it. So still a translation problem or a mapping problem. It's you're mapping image to a linguistic space, language space, and you're just trying to train a mapping function. So as opposed to sequence, which was text in and text out, this is an image to sequence. So you need a different component. In sequence to sequence, you had a text encoder and a text decoder, but now you have an image to sequence task, so you need an image encoder. Instead of a text encoder, you need an image encoder and a text decoder. So the examples of what we want to do is, given an image like this, we want to generate a sequence of text like this, or the other, other nice examples here. So as I said, sequence, you need, well, I mean, it could be anything, but in the old days, we used RNN for text encoder and RNN for text decoder. But here, we're using CNN for image encoder as an image encoder and RNN for an image for a text decoder. So that's the only difference. So you just hook just like how you connected these two RNNs together, you just need to connect these two components together. And we're going to skip show and tell, which was the very first attempt to connect the two, connect CNN, RNN, and then made it work. But we're going to straight move on to show attend and tell. So this one employs attention mechanism between the image encoder and the text decoder. And you should probably be able to imagine how it works, given that you've already learned the attention-based sequence-to-sequence model. So show, attend, and tell came out in 2015, and it's a mix between attention mechanism and image captioning. And high-level architecture looks like this. You have an input image, which will be encoded by a CNN. So this is a CNN. I think they use VGGNet, if I'm correct. So they use a pre-trained VGGNet, and then out of the VGGNet, they extract a 14 by 14 feature map. So this has 196 like feature maps, the fibers, basically. We'll get to that. And then based on those 196 feature maps, they translate it to a text using an LSTM or RNN, whatever. And then you're likely to generate a sequence of words like a bird flying over a body of water. And obviously, because you're using attention mechanism, you can actually see which part of the image was most highlighted or got the most attention when generating each word. So for example, a bird, when generating the word bird, this part was the most highlighted, right? So obviously it kind of knows how to ground image like pixel patterns to text and body of water. Everything except the bird part is all like, highlighted. So kind of knows, Yeah, just like this. So you can either go to so the top row is a soft attention, the bottom row is hard attention, but we're going to just talk about the soft attention, which is the attention that we're all familiar with. So you can see that when generating the word bird, it has highlighted this part. When generating the body of water, body of water, it's all highlighting everywhere besides except the bird part. So quick recap to the sequence to sequence with attention. So in the French English translation example, this was the French encoder or RNN. This is the English decoder. Yeah, again, RNN. And when generating each word, it's an autoregressive generation, right? Or you can see it as a conditional autoregressive language generation, where the condition is coming from this part, the given French sentence. So at each time you're generating each word, you have to mix these or weight sum these four latent variables or the RNN hidden vectors, right? So there are four hidden vectors, H1, H2, H3, H4. You want to weight sum them each time you generate each English word, and the weights, the ratios will be different. So that's the attention, right? So when generating the first word, maybe this could be 0.5, 0.1, 0.1, 0.3. But when generating this word, maybe this could be 0.1, 0.6, 0.1, 0.2, something like that, right? Just like that, what we need is an encoder to obtain image representation. As I said, we're going to use CNN for this. And decoder to generate caption, we're going to use RNN for this. And then attention module, we'll need the attention module to calculate the attention weights or the attention ratios. And the attention will be distributed not across different word hidden vectors, but actually the feature maps from here. So we'll show you the architecture. So yeah, for the image encoding, we're going to use VGGNet. For the text generation, we're going to use LSTM, and the attention module, we're going to use MLP, just like what we used in the sequence-to-sequence model. So remember that when you're using a series of convolution operations, you actually decrease the dimensionality. Starting from 32 to 32, if you're not using padding or anything, this will become 28 by 28, 24 by 24, and so on and so forth, right? And you also remember the concept of the receptive field. So when the upper layer feature map, a single feature map, can actually look at wider pixels compared to this is first layer, second layer, third layer convolution. The first layer, like a feature map, can only look at 3 by 3 if you're using 3 by 3 filter, but the third layer feature map can actually look at 7 by 7, right? So this is another thing. So how does VGG16 look like? So this is VGG16. There's like input, and there's two convolutions in pull, so on and so forth, so on and so forth, and then a bunch of fully connected layers at the end, and then you have a softmax for generating 1,000 image classes, right? Like, no, like predicting 1,000 image classes. So this part, this particular part is where we extract the feature maps from. So here, right after here, what you have is a 14 by 14 by 512 feature map. So so it'll look like, well, actually, yeah, it'll look like this. So 14 by 14 by feature map, and you can also look at it in a different way, which is 196 by 512. So 512 is the dimensionality of each feature map. Actually, I forgot to mute everybody. So 512 is the dimensionality of each feature map, and there are 196 feature maps. So it looks like this. So where you had let me draw it. Where you had, what's the dimensionality of this? Let's just say this is 256 by 256. And I'm not really sure. It could be 120 at 120. I'm not really sure. But let's just, for the sake of argument, let's just say this is 256 by 256. And there will be actually 3 channels, RGB, right? 3-channel RGB. And once you've put this image through all these layers, then at the end of this layer, you will have this one. So after a series of convolutions and pools, you will have 14 by 14 by 512 feature maps. So what you do is you actually spread them out you flatten them. So you have 196 feature maps, 1, 2, 3, 4, 5, 6, all the way to 196 and 512 dimensions per feature map. So once you have this, you can treat each feature map, each fiber, 1, 2, 3, 4, 5, 6, 7, all the way to 19. You can treat each fiber as a token, or actually token embedding. So this becomes a token embedding to your image captioning model. So remember that what you had in sequence, it looked like this and this. So here we use actual text tokens, but now we're using feature maps, the fibers, like this. So this is the only difference. So you have each fibers acting as a token embedding, and then every single time you generate one caption word at a time, you weight sum all these 196 tokens differently. So the ratios will be different from here to here to here to here to here. It's the same deal, right? So the exact step-by-step algorithm is here, but we don't need to go through this. So you can probably imagine that. I mean, this is very analogous to if you have a side-by-side between the classic sequence and image to text, it's almost the same. The attention function is right here, which accepts the previous hidden layer and the token embedding. So previous hidden layer, token embedding. It used to be that this was a previous hidden layer from the decoder side. This is the hidden layer from the encoder side. But now, instead of having a hidden layer from the encoder side, we actually have a feature map. That's it. So that's all there is to it. And then you train it end to end, and then you have a nice examples. So some technical details. We'll skip the technical details. If you're interested, you can look it up on your own time. There are some techniques to make it work and train nicely, and then yada yada yada. So the performance was pretty okay back then. I mean, compared to compared to show and tell, which is, do we have show and tell here? The one the one without the attention. I think maybe it's Google NIC. I'm not really sure. Vinyls. I think this is from DeepMind. Anyway, this is a long time ago. Yeah. Anyway, at least in 2015, this was state of the art. Actually, this was not just state of the art. This was like phenomenal. It was mind blowing because people were just getting adapted to the idea of deep learning back in 2014, 2015, because AlexNet came in 2012, right? AlexNet came in 2012. VGG came out in 2013, I think. And the Word2Vec came out in 2013. GRU-based translation came out in 2014. So translation, people could barely grasp that it works without any domain knowledge. Because if you remember, GRU-based, the RNN-based sequence to sequence, the translation, it didn't require any domain knowledge. You didn't have to even understand the language, the two languages between the encoding side and the decoding side. You just need to have a parallel corpus and then train it, and then it works. So that was pretty like amazing. But then nobody really, well, I mean, not a lot of people knew that you could go multimodal like this, right? Right, like this. Like this was such a mind-blowing study. So, but it's all like 10 years ago. Some examples. So correct examples, let's just look at one. Here, a woman is throwing a frisbee in a park. So when generating the word frisbee, this part is actually most highlighted. So you can see that you can see which fiber is it got the most attention. Based on that, you can actually, highlight these parts like this. So frisbee happened. This is well grounded. The word frisbee and the pixel pattern here, there's a strong connection. So there's like grounding happening. The incorrect examples. Yeah, like this. A woman holding a clock in her hand. So she is just putting on a hoodie, but the pattern here in front of her chest, kind of looks like a clock because there's a circle here, and then there's some like words that circulate the exterior of the circle. So kind of looks like a clock where you can see this is like 9, 10, 11, 12, 1, 2, 3. Yeah. So the model is kind of like getting confused by the confusing pattern. So it doesn't work always perfectly. But which again, not even like modern day vision language models, they don't work perfectly either. So and yeah, step-by-step attention, where how the attention moves or the attention ratios differ between generating each word at a time. So, woman, well, I guess this is a woman. This looks like a boy. I'm not really sure. Anyway, I guess a woman is throwing a frisbee, so this part should be highlighted, but both people are highlighted, so that's a bit unfortunate. And park, everywhere between these two people is, like highlighted again here. And frisbee throwing a frisbee. So frisbee is a little bit more focused compared to throwing, so that also kind of makes sense. So yeah, this is now we're moving on to text to image. So this is image generation. The previous section was image to text. So given an image, you generate text. But now it's text to image. Given the text, you generate image. Again, it's a mapping problem, or you can think of it as a translation problem. Before we go to the full DALL-E 2, which is the text to image generation model, we have to look at CLIP first. So CLIP is I guess a lot of people already know what CLIP is, but CLIP is like it works like a foundation model these days. But when it came out in 2021 in OpenAI, it was kind of like an experiment between how you can experiment on how you can train a model to understand image and text and then ground them or align them in a latent space together. So it's a joint latent space. The way where the latent space is occupied by text embeddings and image embeddings, and there's a strong connection or strong relationship between the two. So they want to learn a joint latent space. So everybody knows this as a CLIP, but actually the title of the paper is Learning Transferable Visual Models from Natural Language Supervision. So they use contrastive learning between text and image, and it has a great zero-shot performance. So when they say great zero-shot, they mean great zero-shot classification. So this is an example. Given an image, you actually can prompt the model with different templates. So a photo of something, type of food, a photo of something. So this is a slot. So it's a slot where you can put different variables or different food name, and the rest, like this part and this part, is a template. So you have a template, and then you generate bunch of candidates using, maybe you have a dictionary or vocabulary. You put different words, and then you see which candidate has the strongest relationship or affinity or cosine similarity, whatever, strongest relationship between this image and the candidate. So out of all the candidates, there could be many, many more. Yeah, there are 101 labels. So there are 101 candidates, and out of all the candidates, this guacamole happens to be the highest highest, like core aligning or has the highest score to this model. So, and the next one is ceviche, but I guess maybe this could be seen as a ceviche. I'm not really sure, but at least this part looks like a guacamole, so it's getting right. Another example here, which is given this image, you have a photo of, a photo of, a photo of, a photo of. So this is the template, and this part is probably like you can put a lot of different place nouns like television studio, podium, indoor, conference room, lecture room, control room, theme park, whatever, gym, wherever. And out of about 400 candidates, this had the highest affinity or the similarity to this image. And this actually works the other way around. Given a text, you can you can actually look a bunch of different images in your training set or in your data set, and then see which image has the highest affinity to this text, and then see which is kind of basically just a image retrieval system or image searching system. So it has a great zero-shot performance like this, because this model was not trained to perform classification. So it's just trained by contrastive learning, which we'll see right now. So has great zero-shot performance, understands relationship in text, image and text very well. So what is contrastive learning? So contrastive learning was actually, was a big thing back in, I'm not really sure, like 2016, 17, maybe. And it was actually unimodal. It was only used for image pre-training, or, like having a self-supervised image model training. So it wasn't used for aligning text and image. It was actually just like image model training algorithm. So contrast learning focuses on positive pairs and negative pairs. So where the positive pairs should be close to each other, it means the distance, and the negative pairs should be apart. And this should happen in the latent space, the representation learning space. So you can see in this picture here, these two pictures or these two images are semantically the same. They pixel wise they're different, but they're both raccoons, right? So I mean, pixel wise they're pretty different. There's like black background here, but there's like bushy, grassy background here. So pixel wise they're different, but in human eyes they're the same thing semantically, as opposed to this, which is echidna, right? So what you want to see happen is when you embed these images into the latent space using the same function, they're all controlled by the parameter theta. So they're the same mapper to the latent space. And when using the same function and mapping to the latent space, you want these two images to be close together. And you want these two and these two to be far apart because they're semantically different. So like this, like this. And you want to see that in the latent space. In the raw pixel space, they might reside far apart from each other compared to these two, because pixel pattern wise, there's like gray brown thing and there's gray brown thing as opposed to the green thing. So in the raw pixel space, that kind of relationship is not preserved. But so what you want to do is you want that kind of relationship, like this relationship, to be preserved, to be respected, at least in the latent space, right? So that's what we want to see. So how you train it? When you want to train a model, this model, to enforce this kind of relationship in the latent space, you need to have a positive pair and a negative pair. And in the contrast learning literature, they call this original image as an anchor image. And there's a positive pair, and then there's a negative pair. And how you prepare a positive pair is just, a lot of different augmentation techniques. You can either grayscale it to black and white, or you can blur it, or you can put Gaussian noise inside, or you can crop it, or you can rotate it, whatever you want. Just as long as you respect the semanticity of this image, then you're good to go. So and then when you put all these images into the same function here, and then there's a distance function which you use to enforce that they should be close to each other, and they should be far apart from each other. And this distance function could be anything. It could be L1 distance, L2 distance. It could be Euclidean distance. It could be cosine similarity, whatever you want. But typically, what people use is this thing called info NCE loss, where you use cosine similarity. I'm sorry, the inner product. So you can, when you look at this, kind of looks like word2vec objective function, or actually softmax operation as well. So kind of like you're trying to increase the probability increase the affinity between these two. So this is the anchor, this is the positive, and this is negative. So you want the numerator to go up as opposed to all the other pairs, all the other negative pairs. So this should be the likelihood of this should go up, or actually the inner product between the two should go up as opposed to all the other normalizers. So that's the high level idea of contrastive learning. So all you need is just these positive pairs and negative pairs, and you need to prepare like millions of pairs, and then at some point your model has a very good understanding between different semantics, like like objects and like different objects basically. So what Clip did is they used contrastive learning to align between image and text, the multimodal learning. So they use cosine similarity, not the inner product or L2 distance, but cosine similarity. And so here you have only one function, which is the image encoder, right? But now you're trying to do a multimodal learning. So you need an image encoder and a text encoder. For text encoder, they use BERT. And for image encoder, they use something called vision transformer. So they didn't use CNN. You could easily use CNN. I mean, you could use anything. For text encoding, you can use RNN, 1D CNN, transformer, whatever you want. For text image encoding, you can use CNN, whatever you want. But here in this particular study, they used something called vision transform, which is a vision model purely built out of transformer layers. And this is the text encoder. We already seen BERT did a pretty good job with text encoding, so they use BERT. So here, this is BERT, and this is VIT, vision transformer. And you can see that when training, or they call it contrastive pre-training, when training with contrastive learning objective, you put a mini batch of text and mini batch of images. So like there are 4, like 1, 2, 3, 4, and 1, 2, 3, 4, right? So you put a mini batch of text and mini batch of images, and these two should be aligned. It should either be a caption or a hashtag or whatever. At least you need to have a grounding somewhere to learn the grounding from. So once you have n number of images, n number of text in your mini batch and n number of images in your mini batch, you can so once you've put it through, you will have n number of text embeddings or text vectors and n number of image embeddings or image vectors, right? And then when you do an outer product between the two, you'll get this matrix. So the diagonal part is the aligning part. So like if this is 1, then this is 1. There's second, this is second, right? You see what I mean? So these diagonal elements should be the one that has a higher probability or higher affinity, which will be this part, right? And all the off-diagonal elements, they are the normalizer. They should go down as opposed to the diagonal element going up. So that's the whole setup. So you're basically trying to, so these are the positive pairs. And so these are the positive pairs in contrastive learning literature terms. And these are the negative pairs. So once you've trained your text encoder and image encoder using contrastive learning, what you can do is like this. So doing a zero-shot classification. You have an image, a query image, and then you put it through an image encoder, then you'll have an image embedding. And then you have a bunch of candidates, what it can be. So yeah, this is a dog, right? So what it can be a plane, can be car, dog, cat, person, truck, bicycle, whatever, a bird. So there can be like many, at least like hundreds of candidates. So you put that into a template like this, and then you put it through an image, a text encoder, then you'll have a bunch of different candidate vectors. There will be n number of vectors, right? And then what you do is you just calculate the cosine similarity between the two. So cosine similarity between the two, here, here. And out of all the pairs, this happens to have the highest cosine similarity, like maybe probably like this, right? Highest cosine similarity, which happens to be the dog. So you can safely say that this is a photo of a dog. And as I said, it could go the other way around. You can put text in as a query, and then you can put a bunch of different images as a candidate and see which one is the right image for this given text. So this is what clip is. So before moving on to DALL-E 2, let's just briefly touch upon this vision transform because we haven't studied vision transformer yet, but this is a very simple concept. So vision transformer came out in 2021, so a lot of things came out in 2021. And the title of the paper is pretty uh, attractive, I guess. An image is worth 16 by 16 words, and transformers for image recognition at scale. So this is the very first work that did not use any convolution operations when building your image classification model. Before this, there were some works that combined attention mechanism with CNN, but this work is the first work that did not use any CNN at all, just pure transformer, and had comparable performance to the most powerful CNN back in the day, back in 2021. Nowadays, I guess nobody actually uses CNN anymore. When you're going upscale, nobody kind of uses CNN. Right, so how does it look like? This is just transformer. We all remember the encoder architecture. The only thing that changed from what we learned back then is the place between these two. So before we had attention first and then normalization, MLP then normalization. But now I guess people found out that putting normalization before multi-head attention and before MLP works better. And you can still see the residual connections. And you put it, I think they used 32 layers of transformer encoder, so which is way larger than BERT-based. BERT-based used only 12 layers, right? So they use 32 layers of transformer encoder. And what you do is do I have it? Yeah. What you have is an image, and then you cut it into grids. You cut an image into grids. So, for example, if you had a 256 by 256 image, then you can cut it into 16 by 16. So 2, 3, 4, like this. And each patch will be 16 by 16. So which means that there are 256 patches or grids in your entire image, I mean, you divide 16, then 16, there will be 16 horizontally. Divided by 16, there will be 16 vertically. So 16 times 16 is 256. So there are 256 patches. Kind of like, where you had the 196 feature maps from the VGGNet extracted. This kind of looks like that. So you're kind of like preparing that kind of feature map to be learned. So you cut up your image into 256 patches, and then you linearly transform each patch. So you just have this image. So this is still an image. This is still a pixel, right? There are 256 pixels in this patch. So you simply just spread it out. You spread it out into 256 pixels. And then if you call this X, then you just do WX plus B, you get a Y. So this is the Y. This is the Y, linear transform. You linear transform each patch, and then you add position embedding. So you can see all the 0, 1, 2, 3, 4, 5, 6, 7, 8, using sinusoidal embedding or whatever. So, and this is the CLS embedding that we learned from BERT. So once you do this, this is very simple. You don't even do any image pre-processing or anything. You just cut up into grids, and then you linearly transform them, and then put it into transformer, and then just push it through 32 layers, and then you just simply take the CLS embedding and then put it through MLP head, softmax classifier, and that's it. So you just train it end to end. Yeah, 32 layers. The hidden size was 1280 as opposed to 768 from BERT, and 16 attention as opposed to, I think, BERT used 12 attention as, I think. So it's a bit larger than BERT-based. So obviously this is a classification model. It doesn't do anything else. Not an image classification. It's not an image generation model. It's not clip, or it's not multimodal or anything. It's just simply purely image classification model. But when you're doing image classification, you can study the attention patterns here, right? So this is some of the examples. So when you're classifying this image into a dog, then this part is highlighted or got the most attention, just like how we see what we saw in show attendant tail. Airplane, this, And I guess this should be a snake here, but the model is making a mistake. So it's because it's highlighting or attending to this part, which is not the object of interest. So this is VIT, and now we move to DALL-E 2. So we've learned clip. So we learned clip where text encoder was BERT and image encoder was VIT, and you did a multimodal training between the two. So now these two encoders or these two functions are aligned so that the outputs are residing in the latent space nicely together, understanding the relationship between the two. So we have a clip now, and moving on to DALL-E 2. So DALL-E 1 was actually an autoregressive image generator, but not a lot of people use autoregressive image generation anymore. People all use diffusion models. So DALL-E 2 was the first, I'm not sure if it's first, but probably the most well-known at the time, back in 2022, back at the time, was the most well-known text-to-image generation model using diffusion, and very high quality at that as well. So you see that you put this text in, a corgi's head depicted as an explosion of a nebula, and then the model can generate image like this, which is fantastic, which is just, you know, um, I again, like revolutionary, I guess, because not a lot of people can draw at this quality, at this level. Maybe, 0.1% of population, maybe, or maybe 0.01% of population. But now models can draw, so which means that models can draw images or paintings better than 99% of humans. So not just this one, like this, Panda, med scientists mixing sparkling chemicals, art station. I'm not sure what art station is. And an espresso machine that makes coffee from human souls, art station. You know, it really understands how to mix the abstract concepts like human souls into an espresso machine, which, well, I mean, who can say that models don't have image imagination? So it's a two-step. So it says that here, text-to-image generation using clip priors. So we've learned clip. So we're gonna look into what clip prior means, and it uses classifier-free guided diffusion. We learned classifier-free guided diffusion, right? CF, we're going to call this CFG now. Classifier-free guided diffusion. Two-step upsampling, which means that you generate low resolution and then you upscale to 256 and then 1024 using diffusion. Diffusion here and diffusion here, right? So how does it work? Step by step. So step by step. So what you do when you're running a already trained DALL-E 2, what you do is you put a text in, the one that you want to generate, such as, like corgi. Like you put this text in, then since you have a clip text embedder, which is BERT-based. It's not exactly BERT because now it's trained using contrastive learning objectives. So now it's a clip text encoder. So clip text encoder. So you have a clip text encoder here. So when you put text like this, you get a text embedding. And so the output will be clip text embedding. And then what you want to do next is you use this clip text embedding as an input, and then you get clip image embedding out. Clip image embedding out. So this could be coming from either this, or you can actually look up from your given image data set, you can look up the most closest image embedding from the clip, so from the clip image encoder. But instead of doing that, you can actually generate clip image embedding. How we do it, we'll take a look at it a couple slides later. And then when you have the clip image embedding generated, you use that as an input to your diffusion model to generate raw image, which is 64 by 64. And then based on that, you can upscale from 64 to 256, and upscale once again from 256 to 1024. So this is the whole step-by-step procedure. So importing, you first what you do is you start from importing a pre-trained clip, which comes with a VIT or clip VIT and clipBERT text encoder. So this part. And what you can do is given a clip text embedding, so you put this text in to a clip text encoder, then you have a text embedding out. You can either, there are option number 1 and option number 2. you can either find the most compatible image embedding, which is image lookup or image search, image retrieval that I said when I was talking about the when I was talking about clip. You can either search for the most compatible image because there you will have a lot of images in your data set, and then you put all these images into your clip image embedder, and then you have a bunch of different vectors, and then you find the one that has the highest cosine similarity with the given text embedding. But that's not what we want to do. That's not because we want to generate a new image. We don't want to search for the closest image, right? We want to generate a new image. So that's what we want to do here. Number two, generate the most compatible image embedding, which kind of looks like the clip image embedding, but not the one that is already in the data set, but the one that we generated. And the way we do it is here. You can either generate the clip image embedding using autoregressive model or diffusion model. Either way, if you use autoregressive model, then you just generate one dimension at a time. Like you generate this, and then this, and then this, and then this, and this using a for loop. This is using autoregressive. First, I mean, you'll have to train the model, but you'll have to train the autoregressive model. But then when you train it, then you can generate one dimension at a time, and then that becomes your most compatible clip image embedding. Or you can use diffusion model. You can start from the text and then gradually, diffuse it, like denoise it into this, again, the most compatible image embedding. And okay, yeah, generate via autoaggressive or generate via classifier free guided, because now this becomes your condition. And when you have a condition, you need to use classifier free guided diffusion. So using this text embedding as a condition, you can either go this way. Well, I mean, if we're using CFD, we're going this way. So both ways, autoregressive generation or diffusion-based generation, both performances are comparable, but OpenAI went with the latter. They just used diffusion model to generate from text embedding to the image embedding. So now we have a brand new image embedding that was not part of your data set, right? So this is a brand new image embedding, and now you're ready to use this image embedding to generate an actual image, which is step 3. Given an image embedding, you'll have to generate raw image, which is 64/64. So that's the given a clip image embedding, generate a new raw image using CFD again. So we're using 2 diffusions in a chain because we used diffusion here to generate image embedding given using text embedding as a condition. So we use diffusion here, and again, given image embedding as a condition, we're generating 64/64 image using, again, diffusion. So you're using 2 dimensions at a time. I mean, sorry, 2 diffusions at a time will chain together in a step-by-step manner to generate final product here. So you could have gone from text to image directly. You didn't have to go through this image embedding and then, like that. You could have gone from text embedding directly to the 64/64 image, the raw pixels, using just one diffusion. That also works well, but I guess the reason that OpenAI people kind of slipped in this part where you generate clip image embedding first, and then using clip image embedding, you go to the 64/64 raw pixels. I guess they did it because it kind of worked better, maybe better image quality, or like more diversity or more alignment between text and image. I'm not really sure, but that's how it is. So when you compare this DALL-E 2 architecture with latent DDPM or stable diffusion for that matter, there's a lot of similarity between the two, because in latent DDPM, you first train autoencoder, encoder, and decoder, image autoencoder, right? You first train image on autoencoder, so there's image here and then image here, and what you're generating using diffusion is this part, the latent embeddings. So you're generating, I mean, and you have a bunch of conditions. You could use either text or representation, but let's just stick to text. So you have text going into the text embedder, which can be clip text encoder, and then you have the clip embedding, or the text embedding out. And then you're using as a condition for your classifier free guided diffusion. But what you're generating at the end here is this. So you need to return this latent embedding or auto latent representation in the autoencoder space, you need to put it through the decoder to get the actual image out. So you're generating using the diffusion, you're generating latent representation, not the actual image. Just like how you generate here, you generate latent embedding, which is now the clip embedding, right? Latent embedding using text as a condition, using diffusion, and then, well, in latent DDPM or the stable diffusion, this part was just an autoencoder decoder. But now here they're using diffusion to return this image embedding into the actual raw pixel space. So that's probably the most noticeable difference between the two. Conceptually, they're pretty much similar, right? Oh, and of course, there is like a upscaling operation from 256 to better higher image resolution than 2024 higher image resolution using diffusion again. But we're not gonna talk about that part. If you're interested in super sampling, you can search the web, and then there will be a lot of nice tutorials and whatnot. So that's DALL-E 2. And now we're moving on to the final chapter of today, which is the Vision LLM. Any questions so far? We're touching upon a lot of different topics, but I mean, you could basically forget about show, attend, and tell. You just need to understand the high level concept. But then clip training and VIT and DALL-E 2, they're pretty recent works, and a lot of findings and techniques developed in that work they're still being used in today's like vision LLM or image generation or video generation for that matter. Like Sora is based on transformer and diffusion at the same time. So, and using gigantic transformer, you can generate like, a high HD quality video of 1 minute duration, purely based on transformer and diffusion. I guess no question. Okay, cool. Oh, actually, no, this is not the llama lava thing. Yeah, I said that if we have time, we're going to touch upon the BERT-based multimodal learning works. This is it. So image text multimodal pre-training. So since like maybe like in the mid 2019 or late 2019, up all the way up to like 2020, 2021, maybe 2022, a lot of work came out that was based on BERT and mask language modeling to train image and text together at the same time, which is, I mean, like video BERT, VilBERT, InterBERT, XBERT, Uniter, Unified VLP, PixelBERT, Coca, Flamingo V. Flamingo is actually a generative model, so you can take this out. But BIT, like they're all based on like BERT idea or mask language modeling. And the objective is all these work objective is pre-train a model to understand the relationship between image and text, kind of like Clip. Clip was also pre-training your image encoder and text encoder using contrastive learning to understand the relationship between image and text, right? This is the same objective. It's just that they're using not contrastive learning, but they're using contrastive learning plus a lot of different things like mask language modeling, object classification, whatnot. You'll see. And the downstream tasks are once you've pre-trained the model, you can use it for a lot of different downstream tasks like image retrieval, visual question answering, image captioning, image generation. But the important thing is you need to fine-tune your pre-trained model for each task. So you need to fine-tune for this or this or this or this. Like for each task, you need to fine-tune your model, which is unlike what we use these days in the LLM era, where you don't fine-tune, you just use in-context examples, right? So the common strategy for all these work, all these studies is extract image features from the image. First, you need to extract features from the image. You can either use a pre-trained object detector like the fast RCNN or mask RCNN, off-the-shelf object detector, and then run that on your image and then extract objects as a feature map, as a vector. Or you can directly feed the pixel feature maps, just like how you fed the pixels to the VIT in a grid. You can do the same thing. Or using VQVA to quantize image into code, but we haven't talked about VQVA, so let's just skip this part. And then feed the image features and text. Text can just go vanilla into the BERT. So you feed image features and text to BERT, and then optimize for some pre-training objective, which includes contrastive learning type of thing, image text alignment, but also masked language modeling, masked image prediction, and maybe some more. So Vilbert, if I remember correctly, is probably one of the very, very first work that tried to use BERT-based architecture to train image and text at the same time. And more precisely, they used videos, not images, not just a single image, but they used video frames, like multiple frames like this. So so you can see the architecture. Let's see the architecture first. So this is a single BERT, but on the left side, you put the images in, and on the right side, you put the text in. And these images are actually object detected. You run, do we have it? Yeah. You run mask RCNN first on your image frame in your video frames, and then extract the objects out as a feature vector, right? And then those vectors go into your left side of your BERT as a token embedding. And then that's it. So, and the text is text. You just put the text in. And this part is pretty easy. So, oops. No, I went all the way to, all right. This part is easy. This is mask language modeling. You randomly mask 15% of your text and then try to guess the identity or reconstruct the identity of your masked parts. But here on the vision part, what you do is you also want to do something similar to mask language modeling, like masking out certain image vectors or image tokens, I would say, image tokens, and then try to guess the identity. But this is pure pixel, so it's really hard to set up a nice mask language modeling like objective using pixels. But in Vilbert, you can fortunately do that because when you're running mask RCNN on your image and extracting objects, you also have a object classes assigned to your objects, right? So there's a assigned probability for example, let me just quickly draw an example. Like if this is your image and there's like a bunch of people, and like maybe a car and something like if this is your image, then you'll have mask RCNN detect this one, detect this one, detect this one. And then when these detected parts will go in as a token embedding or image token. But also, when you're running mask RCNN, each detected object has a class probability. Like out of 1,000 classes, you have like this could be a person. And out of all the 1,000 classes, like this could be a car. This could be a car, like that. So once you have this, you can actually use this to set up a mask language modeling type of task, because once you've masked this one, you can force the BERT model to guess this highest probability and the highest likely class as an output right here. So you do that. And let me erase all these. So that's how it works for the image part. And for the last one, image text alignment prediction, which is kind of like contrast learning. So for maybe like 50% of the time, you put aligned image and text into your model. And the rest of the 50% of the time, you put unaligned, unmatched image and text here. And then for the aligned samples, you take the CLS embeddings and then you do an inner product between the two or something, something. And then you have to have the label 1 for the aligned and label 0 for the unaligned. And that's it. So kind of like a contrast learning. So just like a high level alignment between these images and text. Images and text tokens. So these like mask language modeling and mask image modeling is kind of like a granular low level feature learning. And this CLS, this alignment thing is high level, like, joint multimodal learning type of thing. So you do this, and then you train this for a bunch of iterations, and then you fine tune it for a bunch of different downstream tasks, and you show that it works better. So there's a lot of different, like, variants, like LXMERT, VL-BERT, Uniter, Pixel-BERT, Coca. I'm not going to go through all all of them. If you have if you are interested, then you can look it up. So, but the gist of it is all the same. You have an image encoder. You have a sorry, you have a BERT encoder. Sorry, transform encoder. You have a transform encoder, kind of like a BERT, and then you just somehow put the images in and the text in, and then just use some objective function. Most likely, it'll be mask language modeling, mask image modeling, and alignment function, and maybe something more. But basically, it's those three, and just some variations in the architecture. And well, nobody really well, I wouldn't say nobody, but not a lot of people are interested in this kind of architecture or this kind of training anymore because they all require downstream per downstream task fine-tuning, which is not very wieldy. Right, now the last one, the Vision LLM. Before going into Vision LLM, just out of precaution, uh, I prepared some Llama related slides because maybe I was concerned that maybe not all the people are familiar with LLaMA, but I guess most people are. So LLaMA is a pre-trained language model released by Meta. So the LLaMA 1 came out last year, February, and LLaMA 2 came out last year, July. LLaMA 3 came out, I forgot when it came out. And then there's LLaMA 3.1, 3.2, 3.3, and maybe LLaMA 4 will come out soon. So it's just a series of releases. And the when OpenAI came out with GPT and Anthropic came out with Claude and Google came out with Gemini or MedPalm or Google came out with Palm or Gemini, Meta was doing a different thing and they were kind of late. They couldn't get onto the boat at the same time as those three companies. So they actually took a different route to developing the different route in how to strategize for developing LLM, and that was going open source. So they're open sourcing their pre-trained models, and then they're releasing it to the public, and then now the entire like open source community is all based on Llama. There are a couple more open source models, but Llama is probably the most well-known and most heavily used. So it was a great strategy from Meta. The one that first came out in last year, February, came out in different sizes, 7B, 13B, 33B, 65B, compared to GPT-3, which was 175B. This is a bit smaller. And the context length was 2048. And it was trained on 1 terabyte or 1 trillion, sorry about that. 1 trillion or 1.4 trillion tokens. So the smaller ones were trained on 1 trillion, larger ones were trained on 1.4 trillion tokens. And this was the training data set consists of only 20 most spoken languages based on Latin and Cyrillic. So Llama 1 couldn't speak like Japanese or Korean or Chinese because they're only dealt with Latin or Cyrillic, like Ukrainian or Russian, that kind of stuff. And this is pure autoregressive language model. This is not fine-tuned or instruct-tuned or chat-tuned. It couldn't speak or understand your command. It couldn't execute your query. It's just like GPT-3 vanilla model. But Llama 2, when Llama 2 came out, first of all, the context length has increased and they trained on more tokens. And commercial use was allowed as opposed to Llama. Llama 2, I mean, but bit behind the story, Llama 1 was not actually like open to the public. They actually got requests from researchers and then they shared the checkpoints to only those they approved. But somehow it got leaked, obviously. Eventually these things get leaked. So now everybody got access to Llama. So Llama 2, starting from Llama 2, they just opened to the public from the get-go. And commercial use was allowed. And now they also released chat fine-tuned model as well. Not just the vanilla GPT-3-like model, but also fine-tuned their vanilla model and then made it possible for Llama 2 to have a conversation with you. So they fine-tuned on 100,000 chats and 1 million human preferences. So this would be like supervised fine-tuning, and this would be like RLHF, right? And yeah, we won't go into Llama 3 and Llama 3.1. So when Llama came out in 2023 February, it wasn't able to follow your command. So what Stanford people did is they developed something called Alpaca, which could follow your instruction. It's not a chat, but just instruction following, kind of like InstructGPT, not ChatGPT, right? So people from Stanford, they developed Alpaca in a way that Alpaca would resemble the behavior of InstructGPT based on LLaMA, which could not speak or understand, or which could not, follow your command. So what they did is, you eventually what you want to do is you want to make this follow your command. So what they did is they used a already powerful GPT model, like early ChatGPT model. Using this, they generated a bunch of instruction following examples like this. Like instruction, brainstorm a list of possible New Year's resolution. Then obviously ChatGPT will output these, nice, reasonable outputs. So you can actually generate a bunch of these things, and then what the Stanford people did is they generated 52,000 instruction following examples from ChatGPT. And the way they did it, how they generated 52,000 examples is something called using, do we have something called self-instruct? We'll talk about this. So there's a paper prior to Alpaca. There's a paper called self-instruct prior to Alpaca. So Stanford people used self-instruct to generate 52,000 instruction following samples from ChatGPT, and then they use these to SFT, supervised fine-tune supervised fine-tune LLaMA 1, LLaMA 7B, and now LLaMA can follow your examples. It cannot chat, but at least it can follow your command, and that becomes Alpaca. And they did it with only $600. So if you think about how much money went into developing InstructGPT and ChatGPT, the $600 is nothing. And this is possible because the base model, the foundation model, LLaMA, was freely released by Meta. This is where a lot of money goes in. Pre-training your language model with 1 trillion, 2 trillion text. That's where the money goes, where the money and the GPU and the resources are required. But since Meta thankfully released this, then all you need to do is generate a bunch of instruction following samples from ChatGPT, which only requires like a couple $100. And then given those examples, you use cloud GPU to fine-tune your LLaMA, and that also requires like a couple $100. And all in all, it's $600. So if you know what you're doing, you can only, with $600, you can develop your own little instruction following language model. So right after this, a lot of different variants came out, like Vicuña, Orca. I can't even name them. Yeah, millions of different like small LLMs came out. So what is self-instruct? So self-instruct is the strategy the Alpaca researchers use to generate or extract these examples out of ChatGPT. So self-instruct is pretty simple. I mean, self-instruct is what the authors of self-instruct, what they did is they generated or extracted high quality instruction following samples from ChatGPT, and then train GPT-3 using those examples, train GPT-3 to make GPT-3 better. It's just that here, what Alpaca researchers did is they trained LLaMA instead of GPT-3. Here they trained GPT-3 with the examples, but here with the examples, they trained LLaMA, and that's the only difference. So what's self-instruct? So self-instruct is just like kind of automatic process or like a pipeline to generate or augment your instruction following sample pool with like multiple iterations. So you start with a very small 175 seed tasks. So seed means people actually manually generated or people manually wrote instruction following samples. So the researchers themselves wrote 175 samples, and given this, they put it into a pool. And then from the pool, they randomly sample some number of samples to the ChatGPT, and then the ChatGPT will generate similar instruction following samples. And then based on once the ChatGPT has generated those samples, we can forget about this part, because this part Alpaca didn't use this part. So once LLM generated the similar looking instruction following samples, you put it into a pool. Oh, actually, before putting it into, you filter it out. If the generated samples are too similar to the seed tasks, or it doesn't make sense, or it's too small, too short, too long, using various filtering criteria, they filter some, low quality samples, and the high quality samples go into the pool, and then they do this, they run this cycle for many, many, many times until you have enough number of samples accumulated in your pool. And then using the pool, you can either you fine tune Llama 3 or Llama 2 or whatever. That's whatever you want. So that's it. And some of the self-instruct examples are like this. So you can either do pure instruction and output, or you can have instruction, input, and output. So it depends on what kind of task you're after. If this is like generate a random password with at least 6 characters, writing a code, then that will be instruction and output. But this one, write a story with 3 characters, person, an animal, and an object. And input, person is John, a programmer, animal, a dog, object, a laptop. So you need input as well. And then based on these two, you generate the output. So that's another form of instruction following example. So using these as like a seed examples, you can like augment your pool with many like similar looking examples using the power of ChatGPT. So that was self-instruct. Now we go to vision LLM. So now we know LLaMA, and now we know how to generate bunch of instruction following samples. Then you're ready to build vision LLM, LLaVA. So LLaVA is the very first very first paper that showed how you can train llama to understand images and have conversation with llama about the image, like here. So you put image into the model, and then you ask, do you know who drew this painting? Then LLaVA, the trained model, have a very nice description here, like this. Mona Lisa, it's a work by Leonardo da Vinci and yada yada yada. But now you can do something else. You put a gag image, like a Mona Lisa, but a dog actually. And then you again ask, do you know who drew this painting? But then you understand this is a humorous situation, and it appears to be like does it say Mona? Yeah, kind of like Mona Lisa, Da Vinci. So it knows all the words and it understand this is a parody of Mona Lisa. So with LLaVA, you can do this kind of thing. So how do you train LLaVA from llama, which doesn't have any idea how to understand images at all, or it cannot even have a conversation actually, because no, actually, yeah, conceptually it's like that. So how do we do it? So you need 2 things: language decoder or a language model. So it can be it could be any language model, but in LLaVA, they use Vicuña, which was already trained to have a conversation with you. So Vicuña is a chat model. Unlike Alpaca is an instruction following model. Vicuña is a chat model, so you can have a conversation with it. So you can take any pre-trained language model, and you can take any pre-trained image encoder. In this case, the LLaVA authors, they use clip VIT, so clip trained VIT. And these two, when you have these two, you're good to go. So step one is pre-training for feature alignment. So actually, let's look at the architecture first. So you have a language model, and there's vision encoder, VIT. And all you need to do is slide in a projection layer between vision encoder and the input to the language model. Because your images, once you put your raw image into your vision encoder, then you'll have a bunch of, because this is a transformer, right? VIT is a transformer. So you put image grids, image patches in, and then you'll have the same number of contextualized embeddings coming out, just like what transformer does, right? So these contextualized embeddings actually, they're like right here. They're right here. And you just don't put them directly inside the language model, but you put it through a projection layer, a linear layer that just linearly transforms your your contextualized vector into some other vector, which is this. And then first what you do is you pre-train this layer only. You only train this layer so that only the projection matrix is updated based on subset of conceptual captions 3 million. So a big gigantic image caption data set. Based on that, you only train this layer first, just so that the output from the VIT, this part, and the input to the language model, this part, is well aligned. Because VIT is trained on clip, so it's a clip trained VIT, which has its own latent space. And language model is also pre-trained, so it has own text latent space, right? And you want to make them align. You want to connect them you want to have them well connected to each other, which will be done by this projection layer. Stage 1, you only train this. And stage 2, now you fine tune end to end. So you train this and train this. This is always frozen. Vision encoder is always frozen. You just train this and this at the same time in stage 2 using these two scenarios, but it'll only stick to the first scenario, which is visual chat. So LLaVA is fine-tuned on our generated multimodal instruction following data for daily user-oriented applications, basically just chatting about the image. So LLaVA train stage 1, you use a subset of conceptual captions 3M, so CC3M. So you just filter out low quality samples and you only retain 600,000 pairs meaning text and image text pairs. And then you train, you set up, the old training samples are in the form of, so the instruction, it has to be instruction following type of, it has to look like an instruction following example. So what you do is this part, this is your input. So assistant like this. So human provide brief description of the image, and then you have image vectors coming out from the projection layer here, image vectors coming out, image vector 1, 2, 3, all the way to n. And then after this, you put assistant, insert the CCM3 caption here. So it's kind of like this. So instruction, input, output, but just like that, you have instruction, input, and output. So this is the instruction, this is the input, and this is the output, right? So all your stage 1 training will be following this template. And then you're only training this part, projection layer. So once you're done with that, then you go to stage 2, where you need to have actual chat, like a conversation example, because you want to train your model, LLaVA, to have a conversation with you. So it cannot be just instruction and input and output. It needs to be a series of like taking turns to talk about something. So using MS Coco, which is a little bit more higher quality image caption dataset than CC3M, which includes 5 captions per image and bounding boxes, which is also a nice feature. You use GPT-4 to generate instruction following samples, but not instruction, but chat, actually. So in conversations, detailed descriptions, and complex reasoning, you need to include all 3 types. And they generate 160,000 samples using GPT-4, not even ChatGPT, GPT 3.5, using GPT-4. So this probably costs a lot of money. So let's look at the example here. So given you first need to understand the image so you need to first extract relevant information, textual information from the image, and then feed that to GPT-4 to generate instruction following samples. So here we have caption. There used to be 5 captions, but we'll only look at 1 caption. So the caption of this image is this: a group of people, yada, yada, yada. Oh, actually, there are 5 captions. Sorry. So there are 5 captions. 1, 2, 3, 4, 5. And they're all depicting somehow on a high level. Like people try to fit all their luggages in the SUV, like this. And you can see that there's bounding boxes like luggage 1, luggage 2, luggage 3, luggage 4, people, and car and whatnot. Right? No? So there are bounding boxes. Person 1 have a bounding box coordinate here. Person 2, person 3, backpack, suitcase, bicycle, car. So a lot of bounding boxes. So what you do is you feed this textual information extracted from the image, and then you feed this to GPT-4. And then you ask GPT-4 to have a nice conversation based on this. It's like generate a conversation about this image given this. So, well, actually, the more precise prompt it would be, let's assume that you are given an image, but in a textual form. So this is a textual description of an image that you cannot see. Now generate a conversation example based on this textual information. That would be like the example that you put into a prompt to the GPT-4 to generate conversation example. So this would be the conversation example here. What type of vehicle is featured in the image, yada, 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 yada. So that takes 1, 2, 3 like turns. And another response type is generate a detailed description of the image. And it can do this very well because you have given all the information inside the, well, not all, but like mostly noteworthy, important information inside the image. It has received in a textual form. So GPT-4 can generate detailed descriptions or complex reasoning and yada, yada, yada. So you have that, and then you just train it. Oh, this is the last part. Actually, let's talk about how you train it actually. So when you want to train a model to have a conversation with you, not just follow your example, instruction following is simple. Here, you put your images in, so the or image vectors in, and then what you do here is your instruction, which is describe what's happening inside this image, right? That would be your description. And then you want to have this part out, which is the output, which is the instruction following output. Like this image contains people trying to fit in all the luggage into the SUV. Right? Yeah, that would be the output. So when you're doing an instruction following training, this is the input. I mean, this whole thing goes as an input, and you want to have one token generated at a time on this part. So this is where negative log likelihood losses come from. It's this part. But when you're doing a convert, and that's it for instruction following model. But when you have a conversation model, you need to have a longer sequence. So let's just erase all this. This is your transformer, or let's just vision. This is your vision LLM. You put images in. This is your image, and you put your first question token. This is your Q1, like what is in this image, and then then you have the first answer here, answer tokens here, which is your answer, and then you put another question in. Let me erase some of these. Put another question in, question number 2. Then you want your model to generate the answer number 2. So your previous conversation is all used as an input to your model, and then you're generating the most recent output or recent answer, and this one at a time. And so this is where your negative log likelihood losses come from, and so on and so forth. So after the next turn, then you put A2 here and Q3 here, and then you generate A3 and so on and so forth. So as you proceed with your conversation, your context length will be way, way longer. So that's why you cannot have too long a conversation with modern LLMs, because there's always a context length limit to all the models. So this is how you train a conversation model. All right, so this is it. And this practice session, you will be taught how to train a vision. Well, I think you'll go multiple steps. You'll first like train clip, and then train like do like a LLaVA type of training and whatnot. So please pay attention to it, and then because then you can pass project 3 without a problem. All right, so this is the end of all the class of this week. And if you have any question from Harakim. Many AI services are likely to fine-tune LLMs for their use. I'm curious whether there are representative technical methods to effectively fine-tune these models, or if it's something that must be learned empirically based on given downstream tasks and various conditions. This might be a broad and somewhat obvious question, but I'm curious how you initially approach utilizing an LLM when given a specific task. Yeah, this is too abstract. When you want to run a service, I'm gonna stick to a very concrete use case. So let's assume that you're starting a startup, and then your startup is about providing some service to your user using LLM, and you as a startup cannot build an LLM from ground up because you don't have the resources or the money or the people or the GPU. So you are most likely to use a pre-trained LLM, such as LLaMA or Mistral or Qwen, for that matter, whichever allows commercial use of their LLM, right? So you take them, and then you fine tune you can either just prompt engineer your model and then do a like a shallow service, provide a shallow service to your users, or you can actually prepare a bunch of pre-trained, a bunch of fine-tuning examples that are tailored to your use cases or your service cases. Somehow, how you're gonna prepare those fine-tune examples is up to you. You can either employ a bunch of people and then just manually write them, or you can use GPT-4 to generate a very high quality examples. That's all up to you. But how you prepare them is up to you. But anyway, you prepare a bunch of tailored instruction following examples or fine-tune examples that are tailored to your service, and then fine-tune the model that you got from fine-tune the pre-trained models, such as LLaMA 3 or Qwen. And how you do it is all based on how you want to run your service. There's not just one answer to this. You can either use fine-tuning, you can either use supervised fine-tuning with some examples, you can use preference learning, you can use RLHF. It's all up to you. Usually you combine all those together. You also have to do a bit of engineering with the prompt engineering. You need to hook your LLM to the memory management services like like vector DB. Like there's a lot of things to talk about. So there's not a good answer to this question. Okay, so any other question before we end the course part, the theory part of this semester? I think this is interestingly the smallest number of participants per class that I've seen over the 4 years. And I guess this is because we have a very powerful AITA. So I hope that's a good sign. I hope that's a good news, a sign that AITA is actually super helpful so that people don't need to come to the class at all, which is probably what the future of education would look like. So that was an interesting finding for me. All right, before we end the class completely, so I'll probably never see you guys anymore. So any feedback, any question, any general comment, whatever. If you have something to say, now is the time. Thank you for the semester. Yeah, you're welcome. All right, yep, thank you guys, and you're welcome. And please, I might ask some of you, I guess you are like the 30 of you are the most attentive, most like participating people of this class. So I might ask some of you to have an interview about how you use AITA and how it kind of improved the performance, or maybe it was more effective for the educational purposes, something like that. So I might reach out to a couple of you. Okay, thank you guys. Then good luck with your. I was skeptical with the AITA first, but now I feel more comfortable. Good, yeah, good. Yeah, those are the kind of comments that I want to hear about when I'm having an interview. All right, great job, you guys, and hope you guys all nail the project 3 and have a good. And also hope that you guys learn something from this semester. All right, very interesting class, even though focus on IT security. Okay, great. All right, thank you guys. Bye bye.